Hello students, and welcome to this video on transformations of the absolute value parent function. So these are the same transformations that you learned about on your pink notes. They're the exact same. We're just going to go over them again for specifically the absolute value parent function. So if f of x equals the absolute value of x, then a of f of b of x minus, b times x minus h plus k. So basically, this is going to look like replacing x with bx minus h, and then putting an a in front. So a bx minus h plus k. So then if you refer back to your pink notes, you'll just copy them over. It's the a, b, h, and k do exactly the same thing. So this is going to be a vertical reflection if it's a negative number. It's going to be a vertical stretch if it's greater than 1. And it's going to be a vertical compression if it's between 0 and 1. And again, these are just copied off the pink notes. B, the only one you're really going to see is a horizontal reflection if it's negative. H is your left and right. Let me turn these into little arrows because these sticks are all starting to look the same to me. There. So your left and right. So remember, left is if you see x plus a number, right is if you see x minus a number, because there is a double negative if it's a negative, if it's to the left. And then plus k is your up for plus a number, and down if you see subtracting a number. So now it says to graph the equation in Desmos.com and use the sliders to explore all this. You don't have to, but I do recommend it, and I just want to show it to you briefly so you know what I'm talking about. So this is Desmos.com. It's a free online graphing calculator, and if you've never used it before, it's a good option for you if you just need something to do your homework or studying or something and you don't have a TI Inspire at home. So you can type in your parent function right here, and then you can type the function notation with all the parameters in it. So you can type a f of bx minus h plus k, and then it will give you sliders, and all you have to do, so see my parent function in red and the transformed one in blue. So parent function, transformed function. So you can see what all the parameters do to the function. So I personally think it's kind of a good way to do it. And then so there's your left and right, and your up and down. So I just want to show it to you. I think it's kind of cool. So back to our notes. Label the transformations for each function below, sketch the graph, and give the domain and range. So on our first one, I know from looking up here that I'm going to be going right 2 and up 1. So I've drawn my parent function in there. So just absolute value of x, absolute value of x. Then I'm going to also put this function in my calculator. So here it is. Here's my parent function right there and my transformed function here. And I can see that it went right 2 and up 1. So 1, 2, up 1. And then notice it just goes perfectly diagonally through the little squares, because the slope of this side is 1 and the slope of that side is -1. So it's this perfect little thing. And finally give the domain and range. So remember the previous notes you did, where we said the domain of an absolute value function is always all real numbers. So this one is still all real numbers for the domain. The range, we want to start at the, so ignore the parent function. We want to start at the bottom. In the bottom, the y value of that point is 1. So my range, the lowest value is 1. And then it keeps going up forever. So my y's keep getting bigger. So 1 to infinity, and there's an actual point at 1, so put a bracket, and that gets a parentheses. So there's your domain and range. And if you want to write that in inequality notation, it is 1, so same number, less than or equal to, less than or equal to matches with the bracket, y is less than infinity. So go ahead and give 2 a try, and then you can compare it to what you get right here. So here's my parent function again. Here's my transformed function. It's got a vertical reflection, which makes it go upside down, and it moved left 3 spaces. And then your domain would have still been all real numbers, and your range this time would be negative infinity because it goes down forever. You'll never reach the bottom. And then up to 0. The y coordinate of this is 0. Just like that. Now out of these 2 examples, which should say example 3 and example 4, that's kind of goofy. We're going to do example 4 together on the video, and then I want you to try 3 on your own. So example 4, let me put my parent function back. And then my transformed one, I have a vertical compression, so it's going to get squished by half. And then this goes right 1. So right 1, and then squished by half. So you can copy the points off the graph, but squished by half basically means that instead of going up a whole square like this, I'm going to go up half a square and over. Half a square and over, and so on. And I'm just putting a few dots so that I can make sure I draw my line straight. So then you can see it's got squished like a spring or a bit of Play-Doh or something. That's absolute value of x, and that is this function f of x. And then my domain is still all real numbers. And my range is actually the same. Notice that moving over to the right does not affect the up and down. So it's still going to be 0, bracket, 0 to infinity. And you can write that as y is greater than or equal to 0. Okay, go ahead and give number 3 a try, and then come back and check it. So here's what you should have gotten on number 3. Here's your parent function. Here's a transformed function. It just has a vertical stretch, so it's kind of twice as tall and skinny. Domain is still all real numbers, and the range is still 0 to infinity.